I will start my presentation. I will give you some background. Well, as you know, most of you work in neuroscience. Modeling the brain, modeling neural processes is interesting for both mathematical and biological point of view. Notably, PDEs from stochastic models. So probability theory has provided many interesting PDEs in recent decades. So the equation I will talk about is known as the elapsed-time model, where neurons are described by their refractory period. Unlike Fokker-Planck equations, that we discussed before, are modeled through the membrane potential. In this model, the refractory period is the key variable. So we have a neural network, interconnected neurons. After receiving random spikes, they are stimulated to make other neurons to spike. So these interactions depends on the intensity of the interconnections. So I always like to show this picture because it illustrates very well where is this model located. So we have the microscopic cortical data. So it's typically extract the typical information like the number of cells, concentration of minerals. And from this data, we can construct the microscopic model. So at this level, we have many stochastic models, different ODEs. And from the microscopic model, we pass via refractory density method. So we construct a density to work at mesoscopic scale, which has the advantage to connect, well, mesoscopic phenomena with the dynamics of a single neuron. And from mesoscopic model, we would like to predict the mesoscopic activity, which is the observable thing, the behavior of the network. So let's go to the classical model. This is the first model, the elapsed-time model, which is a H-structure model. So with this, it's like a transport equation plus an exponential decay depending on the intensity of the interconnections. So here the variable n is the density of neurons at time t. With the last times, its last discharge, S. So the refractory period is S. Capital N of t is the activity of neurons, so corresponds to the boundary condition. And P is the firing rate, depending on the refractory period of neurons and the activity. So in the terminology of H-structure models, the age of the neuron is the elapsed time since last discharge. So when a neuron discharges, they are considered to die, but immediately, instantaneously, they re-enter the cycle at the age is equal to 0. So in this setting, the total mass, the L1 norm, is preserved. I will consider that the firing rate is increasing with respect to the age. So this means the more the age, the more probability a neuron has to discharge. Technical assumptions for the firing rate, we assume that it is bounded and it has some minorization conditions, so it cannot be 0, it's not this pure transport. And three interesting cases for this model is the inhibitory case. This means that P decreases with the activity. The opposite situation is the excitatory case, which is increasing. And also we have the weak interconnection regime, which means that the variation, the P with respect to n is small. So a small perturbation of the linear case. So they are sparsely connected. Well, N0 is initial data with natural space to work is the L1 space. And we have the mass conservation property, which is important to make all the estimations of solutions. The steady state problem for this case is pretty easy. It's just solving an ODE and then solving an algebraic equation, finding a fixed point. So in particular, for the weak interconnections and the inhibitory case, we always have a unique steady state. And the main result about weak interconnection, Cañizo-Yoldas, is that solutions always converge to the unique steady state exponentially in the weak interconnection regime. So in general, for strong interconnections, the dynamics is way more complex. For example, in this case, we choose this particular firing rate and we have periodic solutions. with jump discontinuity, so make it difficult to analyze the dynamics in general. Other possible phenomena for the stronger interconnection is we have a multiplicity of solutions. So for the same initial data, we have, in this example, 3 different solutions. One of them has a discontinuity for the activity, and the second one is monotone, and the third one is convergent. So the particular example is coming from choosing a particular firing rate and study a delayed differential equation. So this is the picture for the classical model. So the new model I would like to present is to consider the multiple renewal equation. This means we incorporate the penultimate time since last discharge. We have the last time since last discharge. You have the penultimate one. So in this case, we have a more complex equation. We rename the variable. So in this case, capital N is the penultimate, is the condition activity to the penultimate time. And x of t is the total activity of the network. So we observe in this the motivation of this model is to try to understand the dependence on the previous history of the spikes. There are other models that consider, for example, the last time and average of the previous spike. So I'll consider this simple model to have the penultimate time, or we could also consider the previous one and so on. So in this case, again, we have P, the firing rate. In this case, depends on the 2 edges and the total activity. And of course, we inherit all the notation inhibitory case means decreasing with respect to total activity. Excitatory case is the opposite. And of course, the weak interconnection case. We consider in the natural domain, and we have the same properties, the mass conservation with the double integral. And the first case to consider, the simple case, is to consider the linear case. So unlike the classical model, the linear case, we have many available tools to study the asymptotic behavior. In this case, for the steady state, it's not easy, it's not evident to find a steady state. Because in the classical model, we have to simply solve an ODE, and we find the solution. But for this, I have to solve another transport equation, and I have to verify that you have a unique steady state. So even the linear case is not evident to find the solution. So the first approach, you have for this model is the entropy method. So this is very classical for this type of edge structure models. In the classical model, we have the generalized relative entropy. So we have a family of Lyapunov functionals which are decreasing and makes us estimate different quantities. We can choose the norm, typically the L1 norm, to prove the convergence to steady state. So this is have a problem. Even as a first approach to prove the convergence to steady state, even if we suppose we have a steady state, depending on P, the first problem is that the partial activity may vanish in some regions. That's a problem. And the second problem, to prove convergence, if we would like to prove L1 convergence, we lack a Poincare inequality. Unlike the classical case in the last time model, the linear case, we write the dual problem, you calculate the entropy, and through a Poincare inequality, you could deduce the exponential convergence to steady state. So in order to avoid this problem, we have the Dublin theory. So in this case, under the same minorization conditions, similar to the classical model, we have a unique steady state and solutions converge exponentially when time goes to infinity. So this is a theory of Markov semigroups. So observing the mass is pretty much technical. So this means that you have the minorization condition for the solutions, then all the solutions will converge to the steady state. So what's the idea? The idea is to control the mass transported following with the method of characteristic for transport equation. So The first step is to consider that all the points are transporting into the red region, though P is strictly positive. That's the thing. Everything we are transported, we are decreasing of mass at exponential rate, but we will make sure that after a certain time, all points will reach the red region. And of course, since when neurons are discharging re-enter the cycle, part of this mass returns to the green line. So returns to the S equal to 0. And from this, we could repeat the same argument of transport. So all green lines would also be transported, following with the same method of characteristics. And then all the mass of each green line is concentrated along another point. So we have to make another step to sigma to see the concentration of at other point. And finally, to construct a minorization function, we simply wait another interval of sigma to see the transport of these points. And we construct all the solution will be minorized at this time by this function, this constant. So this will imply the exponential convergence to the steady state. So that's the linear problem. So in order to have some idea for the nonlinear problem, I will focus mostly on the weak interconnections. So how to pass from the linear case to some perturbation of the linear case, we have to study the nonlinear problem. And the first approach, if we fix the total activity, like the same idea of the classical model, but by the method of characteristics, we have this formula. So we have to relate the partial activity at equilibrium with the probability density. So if we replace in the equation, the alternative formulation of finding a steady state is replacing the equation of n, and we will get an integral equation for the partial activity. Why this integral equation is interesting? Because it's in the form of an identity minus compound operator. So even if we fix the total activity, we could apply to the machinery of Fredholm operators. So we have to use the compactness. We need the compactness to conclude the existence. And under the condition, the second equation is other way to saying that the mass is equal to 1, written in terms of the partial activity. So by using this Fredholm theory, we can characterize the kernel of this operator, and we have characterized the range. So we can apply all the implicit function theorem to get how the partial activity at equilibrium depends continuously and smoothly with respect to total activity. So in order to have a steady state for this case, we have to solve a fixed point equation. So remember, with each x, we can solve the linear problem to get the partial activity depending on x. So in order to have a steady state for the nonlinear problem, we have to solve this equation. And in the weak interconnection case, we can use the classical contraction argument to conclude the existence of a unique steady state for the nonlinear case. So it's a classical strategy. So this is correspond to a small perturbation of the linear case, and we have to be sure, thanks to the Fredholm theory, we can conclude the continuity and get the existence of unique steady state, and everything depends smoothly if space is smooth with respect to x. So in this case, in the Sayes period of Cañizo-Yoldas, for weak interconnections, we proved the exponential convergence for the multiple renewal equation. So the idea is simply to consider the Duhamel formulation and then make the precise estimates to conclude the exponential convergence to the steady state. Of course, we have also convergence to the partial activity converges to the equilibrium, and the total activity also converges both exponentially. So some numerical simulations, some interesting phenomena we have to do. For example, in this case, we take this initial condition and this firing rate, and we see we have multiple jump discontinuities, which is new, because typically in the classical model, we have the periodic solution with jump discontinuities, but the other solution, which are not periodic, only seem to have only one jump discontinuity. So this could be explained to the effect of the second time. And then the solution converts to the steady state. So another example, which inherits the problems of the classical model, if we choose this firing rate, we observe periodic solution for the total activity, and we have multiple spikes in the partial activity. So all the difficulties of multiplicity of solution of the strongly connected case are inherited to the multiple renewal equation. And another example is we add some term dependence on the difference between the two elapsed times, which is some stabilization phenomena. So we see some oscillations at the beginning, but at the end, the solution tends to converge to the steady state. So in general, we conjecture that even if the solutions are converging to periodic pattern, the speed of conversion should be exponential. So some open question of this model. Of course, we have to understand the general setting for strong interconnections, as in the classical model. In the classical model, we could construct periodic solution, but only for Sentai firing rate functions. So we've been interested to find a non-trivial periodic solution depending strongly on the structure of the second time. The other important question is what kind of patterns are attractive. So we could see maybe only the periodic solutions are really attractive as a pattern. As I said before, we have to still check the speed of convergence. And finally, understanding the structural solution jump discontinuities, because in general, dealing with solutions which has jump discontinuities might be difficult to study perturbation. For example, we would like to know if the periodic solution with jump discontinuity are structurally stable with respect to perturbation of P. So we have to extend. We have solutions with the linear case. We know that from some perturbation, the solution still converges to steady state, but we would like to know what happens with general periodic solutions. So that's it. Thank you for your attention.
Zenan has a question online, so I suggest to start with your question.
Oh, thank you. Oh, very interesting talk, Nicholas. Actually, I have read your paper, and this is written perfectly. But I have a question. So, could you please highlight, the benefits of incorporating the second elapsed time A compared to, just like simple elapsed time? Are you suggesting it can have periodic solutions only if you incorporate the second elapsed time?
Can you repeat, please, the question?
Oh, yeah. So can we compare the multiple elapsed time model with the single elapsed time model? Basically, what's new in this model?
Okay. So the new thing is, for example, the type of the boundary condition is pretty new, because if you notice, when the last time is 0, we have a change in the role, so the penultimate times goes in the first time. I mean, when the last time is 0, that means the penultimate one becomes instantaneously the last one. So we would like to see, by this new incorporation of the boundary condition, if we see interesting patterns, for example, like the multiple jump discontinuities, for example.
Okay. But if we just have like a single elapsed time, is it possible to have time periodic solutions?
Sorry?
If there's only the single elapsed time, n is function of t and s, is it possible to have time periodic solutions?
Time periodic solution for the multiple renewal, you say?
No, only for the single elapsed time model.
The single model. If it's possible to have a periodic solution for the single model.
Yeah.
Yes, indeed. We have an article. For example, we have in some cases when P is simple, it's a product of two functions depending on the total activity times an indicator function. In this particular case, we can construct some periodic solution by reducing the system to a delayed differential equation. But that does work in that particular case because you use the method of characteristics. But for example, it's still open to find the, for example, if you take a perturbation of this simple P, it's still open to study existence of periodic solutions.
Okay, thanks very much.
Thank you. Question?
It's more a comment. Do you know Volt processes?
Volt processes?
Volt processes, they are the generalization of renewal processes to memory of the interval before, and eventually you have several orders. And I was thinking that maybe your equation is like the mean field limit with Volt processes that are in interaction. That would be interesting. I don't know. Maybe you want to.
Volt processes are the stochastic processes.
Volt, yes, point processes that have a memory. So they have more memories as the renewals. They also depend on the previous interval and so on and so forth.
Yeah, I see some work that incorporates as I said, the last time, and we have a kind of a memory which is the mean of previous spike. I've seen some works of Valentin Schmuth, maybe.
No, but here it's not the mean. It's really what you said, like the previous interval. Really, so you could have a density for the limit where you would depend on the age of the neuron, like the time until the previous spike, and what you called A, which would be the length of the interval before between the two spikes. So that's just a comment that maybe you want to.
Volt processes.
Volt, V-O-L-D.
Volt. Like voltage. Okay. The processes that are related to these Hawkes processes. So because I know that these models are related to Hawkes processes, so it's a modified Poisson processes. Okay, so
it's another family. I think it's not a lot about Volt process. The guy there.
Okay.
Okay, I suggest to discuss later. Are there more questions in the room? No question. So I have one question. Do you think your methodology works if you add, I don't know how to say, you have the choice between an additive noise and a Laplace operator in your...
If we add some diffusion?
Yes.
That's an interesting question. I've seen some theory of we have the H-structure model like this. We add the diffusion, but most theory I've seen is for the linear case. I don't know if there are some works about, for example, we check the last time equation, we add the Laplacian, if we can determine the dynamics for the nonlinear model.
It was my
question.
It
would be an interesting question, indeed.
Okay.
Typically, with this model, we don't need the diffusion. Well, I decided correctly. Maybe if we could add some vanishing viscosity and maybe see the behavior. No, it could be an interesting approach because, for example, in the strongly interconnected case, we have a multiplicity of solution, but maybe if we would add some epsilon Laplacian, for example, maybe in this case we have a unique solution. So we will see what happens when the epsilon is equal to 0, which solution we will recover. That will be an interesting question. With the delay the same. We can, because in this model, we consider that the transmission is instantaneous. But we change the classical model, we change the boundary condition, but a delay, depending on a continuous delay. So in this case, we could avoid multiplicity of solutions because we have determined the solution in the previous interval. And then what happened with the delay is approaching to a direct mass, so it's approaching to an instantaneous transmission. Which solution we will recover? That's an open question.
Okay, thank you. No more questions. So we thank you. Good morning.